Welcome back, and in this video of the Networking Fundamentals series, I want to step through the architecture and challenges of distributed denial of service attacks known as DDoS attacks. Now we've got a lot to cover, so let's get started. Distributed denial of service attacks come in many forms, a few different ways of achieving the same end goal, which is to overload websites or other internet-based services. The idea is to generate some kind of traffic which competes against legitimate connections and overloads the hardware or software providing the service. Imagine trying to get into an Apple store on the day when a new iPhone is released. How hard is it to get into the store and get service? What if you added 100,000 random people who just want to queue for no reason and waste the time of the Apple Store staff? That's the physical equivalent of a DDoS attack. The challenge when dealing with DDoS attacks come from the distributed nature of those attacks. It's hard to identify and block traffic because there can be millions of IP addresses involved with larger internet scale attacks. Dealing with DDoS attacks requires specific hardware or software protections. We won't be covering those in this video. I'm limiting this to just discussing how DDoS attacks work, so the architecture of all of the different types of DDoS attacks. Now, DDoS attacks themselves generally fit into one of three categories. First, application layer attacks, such as HTTP floods, and these take advantage of the imbalance of processing between client and server. It's easy for you to request a web page, but it's often very complex for a server to deliver that same page. If you multiply that load difference by a billion, then you can have a potentially devastating attack. Next, we've got protocol-based attacks such as SYN floods, and a SYN flood takes advantage of the connection-based nature of requests. Normally, a connection is initiated via a three-stage handshake, which I detail in a separate video of this series. Well, SYN floods spoof a source IP address and initiate the connection attempt with a server. The server tries to perform step 2 of the handshake, but it can't contact the source address because it's spoofed. In general, it hangs here waiting for a specified duration, and this consumes network resources. And again, if you multiply this effect by a billion, this can have significant impact on your ability to provide a service. Lastly, we have volumetric attacks such as DNS amplification, and this relies on how certain protocols such as DNS only take small amounts of data to make the request, such as a DNS resolution request, but in response to that, they can deliver a large amount of data. So one example is an attack of this nature might make requests to DNS servers with a large number of independent requests where the source address is spoofed to be the actual IP address of our website. The DNS servers, potentially hundreds or thousands of them, respond to what they see as legitimate requests and overwhelm a service. DDoS attacks are often orchestrated by one or a small number of people who are in control of huge botnets, and botnets are constructed of machines such as your laptop or your desktop infected with malware. Most attacks come from these botnets, which are constructed from infected hosts, and the owners of these hosts don't even realize that they're part of the attack. Now let's look at how these attacks work visually, but before we do that, it's worth reviewing what a valid application architecture should look like. When a website is working as intended, it looks something like this. First, we have a number of servers which provide the website functionality, in this case, catagram.io. These servers are normally provisioned either based on normal load plus a bit of extra as a buffer, or they're built to auto-scale, which means adding more servers when load increases and removing servers as load decreases. Now, these servers run within a hosting environment which is connected connected to the public internet via a data connection, which, depending on the speed of this connection, has a limited amount of data that it can transfer and a limit on the number of connections it can handle. Then our application has users who are using a mobile application to upload their latest cat pictures using TCP port 443. Now this is HTTPS, and these connections move across our data connection and arrive at the application servers. Now, under normal circumstances, the vast majority of these connections will be from legitimate users of the application. So this is how it should work. We have an application, the servers are sized appropriately, we have an appropriate data connection, and our users are accessing the application using this infrastructure. Now let's step through what happens with the various different forms of DDoS attack. The first type of DDoS attack is the application layer attack. Architecturally, behind the scenes we have an attacker who is controlling a network of compromised machines known as a botnet. This botnet, or more specifically the machines which form the botnet, are distributed geographically, and in most circumstances the real owners of these machines have no knowledge that they've been compromised. An application layer DDoS attack, as I mentioned at the start of this video, uses the computational imbalance of client-server communications as an attack method. It's easy, for instance, for the botnet to make simple requests to the application. In this case, a HTTP GET of a page called reallycomplex.php. The botnet floods hundreds, thousands, or even tens of thousands of these requests, each of them directed towards the catagram servers. This could mean millions or more of these really simple requests, which are all requesting our reallycomplex.php page. The issue is that while making these requests is simple, responding to these requests can be computationally expensive, and this can have disastrous effects on the servers. It's like throwing hand grenades. They're easy to throw, but they're much more difficult to deal with at the receiving end. The effect is that our servers or the data connection won't have the capacity required to deal with the requests in total. The fake attack-based requests will prevent the legitimate requests reaching the servers in a timely way, and this can cause performance issues or failures, essentially a general decrease in service levels. Now, as I mentioned earlier in this video, you can't simply block traffic from individual machines because there can be millions of them, and the data they're sending can in many ways look exactly the same as legitimate traffic, and this is why you have to handle DDoS attacks in a very specific way. Now, at this point, let's move on and take a look at another type of DDoS attack. This time, it's a protocol-based attack. So with a protocol-based attack, we follow the same basic architecture where a single or a small group of attackers is controlling a large botnet, and this botnet is constructed of compromised hosts. Now with a protocol attack such as a SYN flood, essentially what happens is a botnet generates a huge number of spoofed SYNs, and SYNs are the initial part of this three-way connection handshake. So essentially, all of these individual machines attempt to initiate a connection with the catagram.io infrastructure, but crucially, they're using a spoofed IP address. Now, under normal circumstances, if these were real connections, what should happen is our server infrastructure would respond back with SYN ACKs, which are the second part of the three-way handshake. Normally, these connection attempts would be from real IP addresses, so IP addresses which are expecting to receive this second part of the three-way handshake. But because our botnet has initiated these connections with spoofed IP addresses, there won't be anything on the receiving end for our servers to communicate with, and so in this case these requests will simply be ignored. Because they're being ignored, it means the connections will stay in this hung state. The network resources which would otherwise be used for legitimate connections are waiting for this second part of the three-way handshake. And because the botnet is providing millions and millions of these fake connections, it can mean that the network resources are completely consumed with these fake connections. And that means that our legitimate connections won't be able to connect into our infrastructure. Essentially, by generating this protocol-based attack, this SYN flood, we're preventing the network resources being used for legitimate requests. And so we're essentially significantly impacting the network capability of this application infrastructure. So because this three-way handshake is designed to work with slower or less reliable connections, our catagram.io infrastructure will wait. It will attempt to connect to these fake source IP addresses. And while these connections are waiting for this second part of the three-way handshake, these resources can't be used for legitimate connections. And so if the botnet is large enough, if it contains a sufficient number of compromised hosts, then it can, in theory, completely take down the service provided by the catagram.io infrastructure. Now let's move on to the third type of attack which I want to cover in this video, and that's known as a volumetric or amplification based attack. Now this type of attack is still orchestrated by a single person or a small group of people, but with this type of attack the size of a botnet can be much smaller because an amplification attack exploits a protocol data imbalance. So a situation where only a small amount of data is required to initiate a request, but the response to that request is much larger. In this case, our smaller botnet makes a large number of requests to a large number of DNS servers. The requests can be made to a large number of DNS servers and be done frequently because the amount of data that it takes to make the request is relatively small. Now the botnet will use a spoofed IP address, and it will use the IP address of our application infrastructure. So rather than the DNS servers responding to the botnet, the DNS servers will all respond to our application servers. Now the volume of data in each of those responses is much larger than the volume of data making the initial query to DNS, and because of this the application servers will be quickly overwhelmed. This will generally affect the data connection to our application infrastructure rather than the application server itself, and this will mean that legitimate application users experience degraded levels of performance because they're competing to use the same total capacity of the application data connection with these fake responses coming in from all of these DNS servers. So this type of attack does impact our application's ability to provide service because the amount of data that our connection provides is consumed, but it's done so in a way which uses amplification. So rather than the botnet being required to consume the same amount of bandwidth as our application needs to tolerate, this type of attack can use a tiny amount of bandwidth to initiate the attack, but consume a large amount of bandwidth on the application side. And this makes this type of attack ideally suited to take down larger websites or applications. So these are three different common types of DDoS attacks which you might come across as a solutions architect, an engineer, or a developer. The important thing to understand about all types of DDoS attack is they can't be combated with normal network protection. So because of the distributed nature of the attacks, it's not practical to implement single IP address blocks. If you're going to block an entire botnet, then you need to block potentially thousands, tens of thousands, hundreds of thousands, or even millions of IP addresses. What's more, if you use a volumetric or amplification style attack, then the actual machines performing the attack might not even be malicious. In this case, if you're taking advantage of DNS servers using a DNS amplification attack, then these servers, from their perspective, are doing nothing malicious. They're just responding to requests. And so you have to be really careful that in order to mitigate a DDoS attack, you're not actually blocking legitimate traffic or impacting your application's ability to provide a service. If you block all DNS servers, then potentially you can have other issues with your application. Now, AWS and other cloud environments do provide products and services which are specifically designed to help you combat DDoS attacks. And now that you're aware of the architecture and how these attacks can impact your application, it's going to be much easier for you to understand these different products and services. Now, with that being said, that's everything that I wanted to cover in this video, so go ahead and complete the video, and when you're ready, I look forward to you joining me in the next.